Fullerenes carrying life on Earth. So what are fullerenes? Fullerenes are basically cage structures made of C60 carbon molecules bearing 60 carbon atoms in alternate hexagon and pentagon patterns. Now, how was it confirmed that fullerenes are molecules bearing 60 carbon atoms only and that it holds alternate hexagon and pentagon structures? Let's look at the story of the discovery of fullerenes. Discovery of fullerenes, carbon molecules with 60 atoms, arose from Harry Potter's research on interstellar molecules. Working with Robert Curl and Richard Smirney, Proto hypothesized that long carbon chains found in space formed in red giant stars. To test this hypothesis, they used a machine called AP2 to study carbon atom clusters, discovering an extremely stable molecule C60 without dangling bonds. Two models were proposed, a flat hexagonal sheet and a spherical structure. Ultimately, they found that pentagons interspaced with hexagons formed a stable spherical structure, and this led to their 1996 Nobel Prize in Chemistry. Where can fullerenes be found? If we talk about space, fullerenes can be found in planetary nebulae, which are basically gas clouds around old dying stars which are approximately the size of the Sun. Or fullerenes can also be found in hot and dense envelopes of evolved stars in space. As far as planet is concerned, fullerenes can be found in some unusual rocks like shungite and fulgurite. Shungite is basically a highly metamorphized coal. Fulgurite, on the other hand, is a glassy rock that forms when lightning hits the ground. Fullerenes have also been detected in deposits associated with two separate events involving the impact of a large bolide, meaning asteroid or comet, on the Earth. We are stardust, a very beautiful notion which we are aware of. Most of the elements of the periodic table and even molecules that serve as a source of bringing life to a habitable zone have traveled from space. But how exactly did they get onto our planet's habitable zones? Perhaps one of the logical explanations would be that it must have been transported to our planet. And if so, then there must have been a good energetic source or carrier required to carry along such molecules down to our planet. So what is that source? What is that carrier? So research carried out by some of the great scholars demonstrated that fullerenes, a cage-like structure made of carbon, is to be well suited to trap certain atoms and molecules within itself. It can enclose noble gases like helium, neon, krypton, argon, xenon, or even noble gases of specific isotopic composition. So to prove the same, an experiment was conducted on trapping helium, a noble gas, into fullerene during the synthesis of fullerene using Kretschmer-Huffman evaporated arc solid and maintaining helium atmosphere. The observation was that there was no exchange of helium trapped in fullerene with the atmosphere, which proved that fullerenes were indeed good trappers. So this observation was explained with the help of Windows mechanism. In astronomy, if we talk about windows, in astronomy it refers to specific regions of electromagnetic spectrum, which would allow astronomical observations that are nearly not folded or not stopped by the Earth's atmosphere. And these windows could be anything, optical, infrared, or even radio, which can enable scientists to collect valuable data from distant celestial bodies, thereby enhancing the understanding of the universe. Here, varying intensity across the observed frequency window is measured using spectroscopic. In interstellar organic chemistry, more these trapped gases can be released by breaking one or two of the carbon bonds during step heating under vacuum. And this is what is known as to be Windows mechanism. Now, let us see How fullerenes or such carbonaceous compounds exactly get formed in space, something called as interstellar process. So it all starts with the formation of interstellar dust, and that starts with dying of a star and birth of the other star. So interstellar dust is basically a small fraction. It makes up a small fraction of the matter in our galaxy. And it does play a very crucial role in physics and chemistry of the interstellar medium and star forming regions. Asymptotic giant branch star is it is a star, and it is created. So this dust is basically created in the outflows of this low mass stars, whose outflows are really slow but massive. So what happens is once most of the envelope is ejected, the AGP phase ends, right? And the stellar core, which is also called as a hot white dwarf, that gradually starts getting exposed. And when it does, we observe a planetary nebula that is visible. Why? Because it is planetary nebula, as we have seen, it is merely gas clouds that arises due to dying of a star. So the chemical reactions and the nucleation in the AGV outflows transforms the atomic gas into molecules and dust grains. So now imagine the carbon-rich stars. For carbon-rich AGV stars, also called as carbon stars, this results in a large variety of carbonaceous compounds. And to date, more than 60 individual molecular species and a handful of dust minerals have been identified in these outflows, including benzene, polyenes, and cyanopolyenes up to about 13 atoms in size. These environments are also thought to be the birthplace for large aromatic species like polycyclic aromatic hydrocarbons and fullerenes, which are a class of carbonaceous molecules that were discovered in laboratory experiments aimed at understanding the chemistry in carbon stars. Finally, let us talk about spectroscopic tools in the detection of cosmic fullerenes. We are having laser desorption laser ionization mass spectrometry, or LDMS, which is a technique that involves vaporizing the sample with a laser and then measuring the resulting ions to identify the specific fullerene compound present within the sample. We have another long wave infrared absorption spectroscopy, which is again a device that is designed to measure the light absorption characteristic of fullerenes. And this method focuses on detecting the characteristic absorption features of fullerenes in IR spectrum, helping to confirm their presence in various astronomical environments. Apart from spectroscopic tools, we have certain space telescopes like Spitzer Infrared Telescope and James Webb Space Telescope, which have been very instrumental in gathering spectroscopic data that indicate the presence of fullerenes. These telescopes can observe distant celestial phenomena and analyze the light emitted or absorbed by cosmic materials, including fullerenes' unique spectral signatures.